Okay, so let's finish this off here by talking about Green's theorem. So Green's theorem is a relationship that we get between line integrals over a simple closed region and double integrals over a planar region. All right, so when you look at, let's take a look at, right, when we did the line integrals, let's just say we need a simple closed region. There's a simple closed region. All right, so this simple closed region, right, it's a curve with a direction we would think of as our C, and the region inside we would think of as our D, okay? So the relationship we get is between the line integral of the function over the curve, the boundary region, and the double integral of the function over the planar region, D, all right, over the area. Now, we have some orientation issues that we saw in the video of line integrals, right? Orientation was important because the line integral in one direction would be positive and the other direction would be negative. All right, so let's start off with some vocabulary. When I have a region, or a curve rather, that I am integrating in this direction, counterclockwise, we call that clockwise positive. Okay. So counterclockwise or anti-clockwise is clockwise positive. If I have a region, again, some blob, closed blob, by the way, and I am going in this direction, which would be clockwise, is called clockwise negative. Okay. Both regions are simple closed curves, so I'll call that C again. All right, both regions are simple closed curves. They enclose an area that we call D. All right, so Green's theorem is the relationship between the two integrals. It has some conditions. The first condition is that C has to be piecewise smooth, is a piecewise smooth. We talked about what that means in the last video. Simple closed region. Closed region. All right, and when we talk about a simple closed curve, actually curve is better, right? Because we're looking at the line integral side first. So I really want to say simple smooth curve. When I talk about a simple closed curve, I'm talking about a curve where you basically traverse the curve one time in a single direction. All right, you don't have a situation where you have something like this, right? Where you don't have a single region enclosed, right? I've got what, 1, 2, 3, 4, 5 regions enclosed there, all right? This one is simple, this one is not, okay? So you have a simple closed curve that is piecewise smooth, so it doesn't have to be a single function. We're going to call D the region bounded by the curve. Okay. And then we're going to define two functions, P and Q, that have continuous first partials. All right, so P and Q have continuous partials on D. Okay. Then we can define our line integral C over C of P dx plus q dy, we talked about this in the last video, as being the same as the double integral over d of, now I have to get this the right way around, partial of q with respect to x minus the partial of p with respect to y. And then that ends up being dA. I don't want to say dd, d of the area. Okay. All right, so you can kind of think of this. The book uses the analogy to the fundamental theorem of calculus, right? I'm not sure I like that analogy, so I'm not going to go any further with it. All right, but Green's theorem gives us a relationship between the line integral and the double integral that we're used to taking. So what that does is it gives us a way, if we have a line integral that's complicated, but it simplifies doing it this way, then we can do it this way. If we have a double integral that's complicated, but it simplifies doing it this way, we can do it this way. So that's really what this is about. Now there's some notation that goes along with this. You'll see in a lot of textbooks, especially when you move beyond this book and Calc 3, when they talk about a line integral that satisfies Green's theorem, all right? So you have an integral on a piecewise smooth simple closed curve, okay? They'll write it this way, and you might have seen this notation in other books, okay? Now, this is specifically for a line integral over a positively oriented curve. All right, so this is for a positively oriented curve. And we look at Green's theorem, when we look at Green's theorem going in this direction, right, from here to here, when we move backwards, we're looking at positively oriented curves. Okay, so let's look at a couple of examples, a couple of different ways that we can apply Green's theorem here. All right, let me just go to a new page. All right, so, all right, let's take a look at this. We'll take a look at the line integral over C of this. We've got 3y minus e to the sine x dx plus 7x plus square root of y to the 4th plus 1 dy. All right, and C is going to be the circle centered at the origin, radius 3. All right, now I would like to use Green's theorem because trying to evaluate each of these individually the way they are, even if we can parameterize, is going to be a bear. All right, so, and e to the sine x, there we don't have a way to even do that. So this is a situation where I have to be told that this is positively oriented. So anytime we're going around a circle, the curve is positively oriented, right? Because we go around a circle, if you think about it, from 0 to 2 pi, we start here and we go around this way, right? So that makes the curve positively oriented, right? And that's right there at 3. Okay, so if I apply Green's theorem, remember this is P, this is Q. All right, so we have to do dP dy. All right, so with respect to y, this whole thing here is a constant, and I'm just taking the derivative of that, so that's 3. And then I have to do dq dx, which again, with respect to x, this whole thing is a constant, and I'm just taking the derivative of that. That's 7. Okay, so I have my dp dy and my dq dx, and since I am going around the circle, I am going to parameterize for polar. Right, so if I'm gonna do polar, then x is r, which is 3 cosine theta, and y is r, which is again 3 sine theta. Right, r is going to go from 0 to 3, right? So from 0 to 3, and theta is going to go from 0 to 2 pi. Right? So when I set up the double integral, I'm going to go from 0 to 2 pi, from 0 to 3, and then the argument says we do dq dx minus dp dy. So dq dx minus dp dy, and then the polar differential r dr d theta. Excuse me. I'm hoping my cough button worked that time. All right, so this simplifies right down. Right? This becomes basically just 4r dr d theta. Okay, and you can, I'll leave the details of that to you. You could even Fubini this one if you wanted to, right? Because I've got r and theta separate here, so I could do 0 to 2 pi d theta times 0 to 3 for r dr. All right, and this is going to end up, when you work both of these out, this is going to end up being 36 pi as the final answer there. Okay, so just remember this little trick here is Fubini. Anytime you've got a function that's factored into two different variables like that. Okay, so in this case, the double integral was much easier to evaluate than the line integral. Sometimes it's easier to evaluate the line integral, so we can use Green's theorem in reverse. So one application of that is finding areas. All right, let me get some room here on the page. So if we're looking for an area, right, so let's say we have just the area of a region, right, the area of our region D, whatever it is, okay, that is just going to be the double integral over D of dA, or 1 dA. All right, so to put that back into the terms of Green's theorem, that means I need my dq dx, I have to remember to say this the right way around, minus dp dy to equal 1, right? Because it has to be whatever is in here. Okay, so there's a few ways to do that. I could pick p to be 0 and q to be x, right? And then I would take the derivative that way. I could choose p to be negative y and q to be 0, and take the derivative that way. Or I could take p to be 1/2 y and q to be 1/2 x, well, negative 1/2 y and 1/2 x. All of them satisfy, but the way that we normally do this is to do the x and the y. All right, so the area is going to be the double integral over d dA All right, and then that's going to turn into the line integral. Again, we want a positively oriented curve over a positively oriented curve of one half of that, right? 1/2, and then x dy minus y dx. All right, and when we're looking for areas, that's pretty much the way we're going to do this. So, all right, so let's do an area. Get rid of random marks on my board here. Okay, so let's find the area. All right, so we have formulas for the area of a circle. We don't have the formula for the area of an ellipse, or at least not an easy one geometrically. So suppose I want to find the area of, or enclosed by, this. X squared over 9 plus y squared over 4 equals 1. Okay. All right, now I can parameterize this. You can parameterize an ellipse in polar coordinates the same way you do a circle. But just remember what the major and minor axes are giving you here, right? The major axis is going to have a radius of 3. So that means that x is going to be 3 cosine t. And the minor axis is going to have a radius of 2. So in this case, that's y is 2 sine t. Okay. All right, so if we jump right down to the third option there, okay, and I take the area is going to be 1/2 the line integral, all right, over our c, which the c is going to be the ellipse, so hang on one second, of x, what did I say, x dy minus y dx. All right, well here, the derivative of, what am I doing here? Okay, so dy dt, so dx dt is going to be negative 3 sine t, dy dt is going to be 2 cosine t. Okay. So when I plug this in here, I'm going to get 1/2 the antiderivative. Now, going around an ellipse is the same as going around a circle. The theta, the radius, is going all the way around, so that's going 0 to 2 pi. All right, so we're going from 0 to 2 pi. That's where t is going, right? T is going from 0 to 2 pi. All right, so what do we get here? We get x, which is 3 cosine t, times dy dt, which is 2 cosine t, minus y, which is 2 sine t, times dx dt, which is minus 3 sine t, and that's all dt. And now if you look at what happens here, all right, let me leave a little space in front of the antiderivative there, so that's 0 to 2 pi. All right, this is going to be 6 cosine squared t, minus minus makes that plus, that's again going to be 6 sine squared t, so that whole thing is equal to 6. So we end up with 6 times 1/2, so that's going to be 3. And then that's just going to be dt, right? 1 dt. So we end up with, what do we end up with there? 6 pi, right? 6 pi as our final answer. Okay. All right. So we can use Green's theorem in either direction. Just make sure that if you're using Green's theorem in this direction, that when you convert from the double integral to this, you have to have a positively oriented curve. All right, that's important. If you don't have a positively oriented curve, you're going to get the wrong answer, basically. Your sign, your SIGN sign is going to be off. Okay. Okay, so we can extend Green's theorem to the union of regions, all right, as long as they line up in a very specific way. So if I have a, let me do this. All right, so if I have one curve, let's say on this side, that goes in this direction, right? So it's going to go this way. Whoop, that's wrong. Okay, hang on. This way and back up here. So that curve, I'll outline that in red, right? That curve is going this way. All right, and then I have another curve over here, C2, which is, I'll do it this way, going this way. And then it comes down here. So I'll outline that one in blue. So this curve is going, come on, actually draw for me. This curve is going this way. All right, like that. If you look at what's happening here in the middle, I know it's getting messy, but if you look at what happens here in the middle, on C1, evaluating this curve from here to here. On C2, I'm evaluating it from there to there. And if you recall from the last video, when we change direction like that, we end up kind of canceling out. So if I call the one on this side C3 and the one on this side C4, C3 is equal to negative C4. All right, so whatever the integral is along C3, it's the negative of that along C4, so when you add them together, you get 0. All right, so we can basically think of this as one big curve just going around the external part here. So if I have, this is D1 and this is D2, all right, then our whole D is the union of those two. Right, which makes our whole C, C1, I'm just going to say C1 union C2, right, because C3 and C4 cancel each other out. Okay, and again, we still have Green's theorem, so we still have, because this is a positively oriented curve. All right, but our curve now is just this, P dx plus Q dy. And since the union of these two is the boundary curve, all right, what's enclosed by the union of those two is D. All right, so we can come over here and say we're still looking at D. All right, dq dx plus dp dy dA, like that. All right, so I have one, which I believe, yes, last example. Okay, this is literally our last example. And it is also literally the last page in my notebook. See, if we were in class, I would hold it up and show you that it was the last question in the notebook. All right, so I have this labeled as number 12, so I'm assuming this is in 6.4, number 12. I don't have the book open in front of me, so I can't attest to that exactly, but let's see what happens. All right, this problem is given this way, as we have a vector function, fxy, is e to the negative x plus y squared and e to the negative y plus x squared. And my c, my curve is going to be y equals cosine x from the point negative pi over 2, 0 to pi over 2, 0. And then end from pi over 2, 0 to negative pi over 2, 0. All right, so let's see how to interpret this. All right, this right here, this end right here splits up our two curves. So we have one curve here and we have one curve here. Notice the curve here is just a straight line. All right, so if we look on the xy axis, right, negative pi over 2 is on this side. Pi over 2 is on this side. Right, so the second curve, negative pi over 2 is on that side. Right, so this curve over here from pi over 2, 0 to negative pi over 2, 0 is simply, I am actually going to, let me make this a little bit thicker. Okay, is this from here to here, and that is going in that direction. All right, this curve here going from negative pi over 2, 0 to pi over 2, 0 starts here. Right, the cosine hits a top up there at 1 and then comes back down again there, and that is going in this direction. Okay. All right, so that is the region that we're looking at. Now notice this, right? This right here is clockwise negative, isn't it? This is clockwise negative. And in order to apply Green's theorem, we need a curve that is clockwise positive. So when I calculate the integral over c of f dr, right, f times dr, f dot dr, all right, I have to reverse the direction because c is going the wrong way for me to apply Green's theorem. So in order for me to do this, I have to take the negative of the integral, and then I'm looking at the negative of c like that. All right, and then I can apply Green's theorem, p dx plus q dy, like so. All right, so I end up here with again, the negative, and down here, negative c. And this is going to be p, which is going to be e to the negative x plus y squared dx plus q, which is e to the negative y plus x squared dy. All right, so I can write it that way. All right, and once I write it that way, I have a positively oriented curve. So I've got the line integral going the way that I need it to go. Okay. All right, so to evaluate this now, I can apply Green's theorem because I have the integral going the right direction. All right, so this is going to end up being negative double integral. All right, so I have to do, I'll write it this way this time. I have to do d dx of q, so that is e to the negative y plus x squared plus, no, minus, because I always get that wrong, minus d dy of p, which is e to the negative x plus y squared. All right, and then this becomes dA, right, over the area that's enclosed by the curve. All right, now in order to get the boundaries, all right, let's look at this, right? This is our D, this is our area now. All right, so let's look at y. Y, if I go do the top to bottom thing here, right? Y is going from the curve to 0, to the x-axis. So y is going to be from 0 to cosine x. And then x, right, if I collapse this down to just the x-axis, is going from negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2. All right, so I end up then with the double integral. So let's do dy dx. It actually doesn't matter which way we go with this, but I'm going to do dy dx. That's why I did it this way. So that means x is on the outside. Actually, yeah, I have to because I collapsed it down that way. So x is on the outside, so that's minus pi over 2 to pi over 2. And then y is going from 0 to cosine x. All right, now the derivative with respect to x, that's a constant, so that's just 2x minus, here I want the derivative with respect to y, so that's a constant, so that is 2y. And then we're going dy dx. Okay, so you can probably evaluate, well, you know what, let me do it because the second step's a little tricky. So this is going to be negative, and then negative pi over 2 to pi over 2. So we're going to get 2xy in here minus y squared. Okay, I really hope my cough button is working because I just sneezed. Okay, so this is going from 0 to cosine x dx. So that is going to give us over here negative pi over 2 to pi over 2. All right, 2x cosine x minus cosine squared x. And I just wrote this out to this point because I just wanted to point out here, most of the integrals we've been doing have been pretty straightforward. This one you have to do by parts. This one you have to do with the half angle. All right, and when you apply all that and work out the bounds, you end up with a final answer of pi over 2. All right, so those are some applications of Green's theorem, and that is actually the end of our course.